Hey, John here. Let's take a look at this file here. This is the register implementation, the register interface for the VDP of the Z80 Nouveau project. A big thanks to my VIP patrons. Thank you very much. Thanks to everybody that views and likes and subscribes to my channel and all my Patreons. Thank you very much for supporting my channel. See the links in the video description on YouTube for more information on how you can support the channel by becoming a patron. Alright, so we're looking at this interface here, which is an implementation of this part of the manual for the VDP. We're on page 16. Here's what the cover looks like. I got links to these manuals and stuff where you can find them on the GitHub repo for this project, which is also linked to in the description below this video. Alright, here we go. How do we talk to the VDP? I've gone over a lot of this, by the way. There's a whole series on using the actual chip in my Z80 Retro video series. Again, more links below the description on YouTube. So how do we do this? It has 8 registers that are write-only. It also has a status register. I'm not worried about that in this module. This is only going to implement these write-only registers that you can use to configure the VDP. The way this thing works is you have these 2 bytes that you write to the VDP in order. The first thing you do is you send the data you want to save into the VDP in mode 1, the write, and the reading and writing in the mode stuff is over here. So we're in mode 1 and we're doing a write. You send the data to the VDP, not to the register yet. The second byte that you write into the VDP includes the register number within which you wish to save the data that you already sent. And these 2 bits up here have to be a 1 followed by a 0. And this is more, it'll become more apparent why you need to do things like this later on when we get to talking about writing to the VRAM registers, which is documented below here. You'll see there's a different pattern for this and a different pattern for that and so on. So these 2 bits tell the VDP why you're doing this, okay? It needs to tell it where the data is ultimately going to go. And as you can see, the writing into VRAM has 3 bytes in the sequence, not just 2. Okay, so that's what we need to implement. So it screams, let's have a state machine. The first byte will be staged somewhere, and then there will be a second byte that we use to dictate where it's going to go. And I'm going to implement basically an array of registers, and then I'm going to use the register number as an index, a subscript into that array, okay? Now let's look at the output of the test bench first, because this is, we're getting to these non-trivial things at this point. So let's make sure that we can see where we're headed before we try to get there. What do we got? We got our free running clock, and this is the video display processor. So this clock is running in the VDP domain. This is the pixel clock. And we're running at 25 megahertz to generate a VGA signal ultimately, okay? So we assert reset. Reset goes through here, and you can see these are the register values down here. Some of these, it'll be more obvious what these really are in the code, but this is, write 0. This is the staging latch where we're going to store the value here, the data write. This is, I call it write number 0. They got 1 and 2. I got 0 and 1. Yeah, well, okay, that happens. It's TI, so I'm surprised they didn't do byte 2 before they did byte 1. In any event, I'm moving right along. So what happens in the reset is we're going to reset our state. You'll see we have a two state machine here. The first state is it's collecting the data value. The second state is when it's going to store that into the register. So you see, this update reg tick. Notice the state goes high here, and then in the latter half of this thing, during the second byte transfer, this thing then goes 1 over there. So this is, the first state, And the second state is when these are both high, all right? So the way I did it. You can see it going rapid fire over here when I do the testing to make sure that if the CPU wrote data faster than the CPU can write the data, it would still work. So our VDP implementation in our FPGA can run blazingly fast in contrast to the actual TI-99 VDP, which there's no way it could keep up with this rapid rate of data transfers, okay? Because of this, we can do things like use otter instruction while we're running at 20 megahertz on a CPU, and it would not be a problem. And even otter can't go anywhere near this fast, okay? An otter instruction will have on the order of 6 to 8 of these clocks between each transfer. So this is testing to make sure that even if we ran it faster than we could ever go, it will still work. So what happens here? You saw the manual. The first thing you need to do is write out a byte value that you're going to store in a register. And in this test case, that will be this. The second one you write out is the register number here. And the most significant bit is set to a 1. So that's this over here, this 1, 0. Okay? So in hex, an 8, 0 is that most significant bit is on, all the other ones are 0. So what we're asking it to do by sending an EE followed by an 8, 0 is store the value EE into register 0. And if you look down here, here's register 0, and surprise, surprise, it turns it from a 0 into an EE, like this, okay? And then you can see the other test cases in here, and you can either bunch them together or spread them out, and you can see that the values are going into each one of these registers. So what do we got? We got an EE80, a 3383, and you can see this here goes into register 3. We got a 4484, which ends up storing the 44 into register 4. And then what do we got in here? Probably a 55. Yeah, 55, followed by an 85. And these tests were done to make sure that even if the transfers were as quickly as possible, this one down here doesn't even seem possible. It's a half a pixel period in there. Oh, what I've done here is wow, that's a weird test case. This is actually one that would not likely happen. This is when I've sent the 55 late. So I'm not, usually would start over on the leading edge of the clock, but if I started sending it late, it's still going to work. I suspect this is a bug in my test case, because this is not really going to happen, because the leading edge of this clock is when everything is timed off of. And I did it twice in here. We could look at my test case to see if I messed it up or if I did that on purpose. In any event, as long as we make our setup time, we're fine. And it's only running at 25 megahertz. So this is what, 20 nanoseconds or something like that, which is plenty long for an FPGA. In any event, you can see this thing, the values going in. And here's a 6686 that ends up in register 6. All right, and then what do I do over here? A bunch of cockamamie things. Yes, so you implement yourself a clone of a circuit, and you eventually figure out that, you know, all the things you missed when you read the manual. Like, what would happen if I stored a data byte, and then the CPU somehow gets reset, but the VDP is not reset? Well, then my VDP would be stuck waiting for a register number in the next, time you write into the VDP. Well, if that's the case and the CPU doesn't know that the VDP is in that state, how do you get out of this situation? It'd basically be permanently messed up after that. And if you run through these scenarios in your head, since this is write only, you can never really work your way through this to figure out what state it's in. So I think their designers kind of figured this out as they were going along, and that's why I have this read tick signal involved in the registers here. These registers are write only, you cannot read them. So why did I put this in here, and why do you see a read tick pulse in here? Well, it turns out that every time you read the status register in the VDP, it resets our state machine. And you can see that when I store the byte value into the, the storage register, the write 0 register, which is right here. You see it plop down in there. When that happens, and you see here the state changing when that happens, if you then assert the read signal, so that you can, the CPU would be reading the status register, it will reset the state machine. So right here, the state machine goes back to the same state it was in over here. That's how you can ignore this byte. And the only reason this can happen is if you screw up in your software, or you have an interrupt handler that decides to come in and read the status register while your software is plodding through doing these pairings. This is a crappy design flaw. This is this is bad. You would not want to design a chip this way. This is not fixing the problem. This is a band-aid. This is crap. Because if you had an interrupt that triggered after you did this, and it read the status register, then you wrote the register number down in here, which is what would happen if you snuck one in between here like this. Now you've missed a write to one of those registers. So no matter how you slice this, this is crap. Okay, so they band-aided it a little bit. This is useful. Every time you go to write a bunch of values into registers like this, what you should do before you do anything is just read the status register and then rifle through these things as quickly as possible, hoping that there won't be an interrupt between there that will cause your state machine to reset and do weird things and become out of whack and end up, in this case, what you would do is you'd end up throwing away one of the register values. Or worse, you could get it stuck in that state permanently, and it would just always be off, and you'd be writing weird, wonky values in there, okay? Again, I'm not gonna defend this terrible choice. That's the way it is, and I'm replicating the behavior, and there you go. So that's my test case to check that it's happening. So this is useful in case you've ended up in a state where you've forgotten in your program what state the chip is in. And that, honestly, that can happen a lot. If you hit Control-C while your program's running, even if there is no problem with interrupts and stuff like that, your program could die in the middle of writing the register value and then never get to the point where it writes the register number, the would-be register number over here, okay? And then later on, you're reading this thing and so on, it gets wonky. So in your programs, you write a VDP program, what you should do before you write to any of these regs is read the status register. That is my takeaway from this episode of hacking and designing this thing. Okay, so I want to make sure that it does in fact reset it. You can see that the state has become reset, which we'll see when we look at the code in a minute. That's stored in the state reg, so it goes back to state 0. Here's another register data followed by the value. That what am I doing? I'm storing it in register 1, so reg 1 gets replaced with what it was. I guess I never stored anything in there. It becomes an 11. Then we're idle for a second there, or one clock period, a 25 millionth of a second. Then we write an F0 followed by an 86. And you see, I'm sorry, that's an F6. I'm going to have to adjust my glasses. So that ends up getting stored in register 6. Then we're idle, and then we do the status read while idle, and nothing's going on. So this should not change anything. So this test case is if the state machine is ready for a data byte, and I read the status register, is that still going to be okay? It doesn't do anything wonky. No, it does not. It has no effect. It should not have an effect in that situation. I then write out a value. I wait a long time, and then I write the register number, and you can see that goes into register 7 over there. So this is where we're heading, okay? The one observation that I didn't hear in my head as I play back my words is that this module only implements a set of registers that can be written using this protocol that they define over here with the wonky status register reset logic. to reset our state machine. Okay? Now, the registers that are used by the VDP, all 8 bits of every register are not used. I mean, if you go scroll down a little bit from here, you can find the actual registers and which bits are used for what. So, like register 2, you only have 4 bits are used, the other 4 are not used. Register 3, the whole thing is used. Register 4, only 3 bits are used. 7 of the 8 bits are used in this one, 3 bits, and so on. And I have implemented my module so that all registers have all 8 bits. And you might argue, okay, that's a waste of resources, or could be, depending on how you use it. Well, it turns out, here's our implementation. I've said this on my channel before. What happens is, while I do output 8-bit values, and I store 8-bit values in this array here, or more accurately, the 8-bit vector here, the array of vectors, yes, all the registers have all the bits, but if nobody ever uses these bits, then the flip-flops that are represented in this array of vectors, those are pruned out of the design. So they're optimized away if they don't get used. So this is really convenient for testing because I have all 8 bits. It's easy to recognize when you're looking at a test case in hex. And it also, we know that it'll be optimized out when you actually compile it for realsies. Okay, so what do we got here? Process 2-byte transfer from the CPU, yes. Note that read tick is used to reset the write transfer state. All right, that is a feature. I already beat that horse. Okay, as usual, we got a clock and a reset, and this clock is the VDP video domain running at the VGA pixel speed. There's your write tick and your read tick. This obviously should be used to consume the data on my data input, and it's either going to be stored in the write register 0 we saw in the test bench waveform. That's the staging register, or it is going to cause it to take the value that's on the data bus and use it to dictate the register number within which you're going to store your value that you've cached away in this flip-flop over here. All right, so what do we got? We got our 8 registers. We have an update VDP reg tick signal. We're going to generate this in our combinational logic, and we're going to set it to 1 when it is time to save the data, as I said before, in this little cache, the staging register here, into the place that's, the VDP reg, whose number is given by the least significant 3 bits of DN, because that's what this thing says to do. Up here. Oops. Oop. Where is it? Right, somewhere in here. These 3 least significant bits right here. Okay? And remember that TI likes to number their stuff backwards. So these are the LSB, least significant bits. Okay? All right, now the state register here, we have 2 states. It's a single bit. Okay? When it's a 0, what that means is the next time we have a write tick, we take the data on the DN bus and we store it into the write 0 reg and cache it away, because that's the data byte of the 2-byte sequence. Otherwise, what I'm going to state is 1. It's time to write the value that we stored away in W0 reg here, a little cached away thing, into the register that's specified on the data bus DN right now. Okay? And that's where this comes in. And you saw it in the waveform diagram. When state reg is 0 and you see a write tick, we store a data in here. And then after that, the next time there's a write tick, this will go true to let this guy, you can see it right down here, right? That let this guy know that he needs to store the cached value into the register given and the data bus right there. Okay. And that's what we saw happening in here. Here's a perfect example. Here's the state reg here. It's 0. We receive this, and there's my right tick, okay? So it changes state from 0 to a 1. And the next time we get a right tick, we see that state is 1. That's when this thing goes high. This is just the and, ultimately, we'll see, of the right tick and the current state. If they're both 1s, then we say this is when this thing goes true. And on the next leading edge after that, that's when the value goes from W0 reg into the target register, okay? All right, so let's look at this thing here. Here's our sequential circuit. If we're resetting, we clear out the reg, we clear out the state, and then I iterate through all 8 registers in here. Remember, a for loop in Verilog is really kind of a macro. This thing is going to unroll this loop. This is just going to store 0 in every one of the 8 VDP regs. This will have the convenient side effect of blanking out the screen. It'll go black, and it'll disable all the IRQs because there's a bit in one of the registers that when it is 0, a screen is supposed to be blank. And there's a bit in one of the registers that enables the IRQs when it's 1 and disables them when it's a 0. So by just zeroing everything out, we have a convenient side effect of really doing what we want. Most likely, you do not want to have interrupts going nuts, and you don't want to have garbage all over your screen. You can go ahead and put garbage on your screen in your software by simply turning the screen on and storing junk in the memory if you really wanted to do that. Okay, in reality, there probably will be junk in the memory when you start it up. All right, so what else do we got here? When we're not in reset mode, we always, what we're doing is we're copying the usual thing. Copying the next value that we get from our combinational circuit here in our state machine to the reg, and the same way with the state. And I already talked about this to the point where I think you get what's going on there. When this is true on the leading edge of the clock is when we store the cache value in the register. Okay, how do we do this? Not too bad. What do? We say write 0 next is exactly as I said a minute ago. If right trick is true and the state reg is currently 0, then put the value from D in, this is the data bus from the CPU right now, into the register, because write 0 next goes into the write 0 reg up there on the next clock, okay? And if this is not true, I'm either not in state 0 and or it's in state 0, but it's not asserting the tick, just leave the value in the write 0 reg alone by just saying keep it the way it is. All right, so that's what that's doing. State next. What does this one do? Whenever write tick is true, we simply flip it back and forth. Every time we write, we go to whatever we're not. And when we're not ticking, we leave it alone. So all this really does, as it says right here, toggle the state every time I write. Now, if someone's reading for some reason, remember the read tick thing I'm talking about, which normally would be true. We'll see when this gets used in the bigger context, this read tick is not, the CPU is reading anything. No, this will be when the CPU is reading the status register of the VDP, will this read tick go true in this module? That will be the signal when you create an instance of this thing. That's what you'll pass in here. So when that happens, we just slam state next equals 0. We ignore what this thing did, and we just say it should be 0. Now, you could have written this. You could have said, if read tick state next equals 0, else this. Or you could put another question mark in here and do it however you want. I decided this was, pretty readable, so I went this route. And it's this point where I realize I misspoke when explaining this. This simply decides what value to put into the write 0 reg, okay? And yes, there's an and in there that's just like the one here. But this one, I expressed it differently. This is a bitwise and this is a logical and, because I have a comparison in here, that's why. This is the tick signal here that's true when I'm writing and the state is 1, okay? and when the magical 2 most significant bits are the correct value that they should be. Okay? Then I want to say on the next time that there's a cycle of the clock, that's when I should be taking the value on the data bus and storing it into the register here. Okay? That's what that's doing. And here, what I've done, this was kind of annoying. I forgot when I designed this thing that you cannot have a port in regular Verilog. I can't say, all the regs. I can't have an array of vectors as an output port on a module. There are things about Verilog that, I kind of shake my head every now and then. It's like if the person that designed the language knew anything about computer languages, it wouldn't suck this much. Okay? There are a lot of things that are like, did this person ever write a C program in their life, or an algo, any program in any modern language before they decided what would be the limitations of this language? And this really screams that, I think in System Verilog, which is the next version, they decided to give it a name rather than adding a number. Again, these people ever are they part of the world where people write software? I don't know. Sometimes that happens. A very pen and pencil, engineer style feel to things. OrCAD really made me feel that way. And there's aspects of like Altium that are like that too. And I'm like, wow. You know what a namespace is, people. Hello. In any event, this one just screams, I wasn't paying attention when I created that limitation here, okay? This is just one more reason why we might want to upgrade to System Verilog at some point in the future. Again, one of the reasons I chose to use Verilog for this and the project I'm working on here is because System Verilog is not completely supported in the tool set that I'm using, and the code that's flying all over the internet, huge amounts of it, are written in Verilog, and System Verilog is a proper superset of Verilog. So we're learning the basics here, and we're implementing the things we're doing using the basics. There's nothing wrong with doing it this way, but this is one of the nuisances that goes away when you upgrade. So, so be it, okay? Now, there's another issue that comes up. If I did want to look at, or if I made this an output port that was a whole, an array of vectors like this, there's an interesting side effect that also comes in here with the VCD files from the simulation. And hey, I hope somebody gives me a smack upside the head on this one. As far as I can tell, I cannot. Look what's going on in here. I'm in the unit under test, which is an instance of the module we're looking at, and nowhere in here am I allowed to select the VDP regs array of vectors. I can't look at it in here. I can't open up an array in this thing. I can open up a vector, but I can't open up an array. So this is weird, okay? The whole notion of arrays and vectors is weird, but that's a whole nother story. I digress. I'll leave that aside. In any event, it's convenient for the waveform viewer and required, apparently, in Verilog that if I want to send out a bunch of registers, I got to send out a bunch of registers. I can't put this here as a port, okay? Therefore, I have to make all these assignments out here to R0 through R7 in order to get it out of the darn module, okay? So, again, this is the feature set of the language level that we're working at here. Let's take a quick look at the test bench that we ran. Now, this harkens back to some of my earlier, FPGA videos when I talk about creating assertions and displaying things and stuff like that. And I haven't done a lot of that in this particular project. I've just written some that allow me to see waveforms so I can see that my stuff works, and then I move on. This one seemed appropriate. I think I had some trouble with it at one point. I screwed something up and said, let's just clean this up. and add some assertions in here. So this is an example of how you probably really should be writing your, your test benches. And again, in system Verilog, there's a built-in assert function, and in here we have to use a macro because the older version doesn't have it. Again, have they ever seen a program in any other language? I guess not. Okay, so what do we got going on here? A free running clock. We got our initial, and this is a style I explained once before, which I think is easier to use. Now, in here, I do two things. I don't know if I've talked much about this yet either. I reach in to variables in modules that have been created. This is a variable that's not in the scope. Well, it's in scope, but it's not defined here. Now, normally you're going to just interact with and look at these things here that are local variables in your module that you're messing around with. But look what I've done here. Here's my interface. We just look at that code. I called it UUT in the scope of this module that instantiates an instance of this guy. Okay, says here's the things I want to connect up. These are signals that go into the unit under test. Notice none of the outputs, namely the registers, are in here. I just ignore them. I could have defined all 8 registers up here and then connected them all up on here, but I didn't want to do that. So what I do is I reach in to that UUT instance, that module I created. So just put this dot, and then R0 is the name of well, in this case it's a port, but a name of a variable inside that module. And remember, the triple equals means, is it equal to 0 and exactly 0? None of this, question mark, X, Z, all that other crap. No. And in simulation, I want to know that it was set to a 0 after I reset it. Okay? Every one of these should be set to 0 after a reset. And this asserts that it's true. If it's not true, look what happens up here in the macro. It says if the condition's not true, it then will display a bunch of junk out here, give me the name of the file and the line number of the file that that represents the assertion that it failed, and the time over here in the simulation where that happened. Okay, so that's what I did here, and this is probably, as you get to the as you hone in on the final version of a project and you're doing your test benches and stuff, you might want to add stuff like this so that you can just run these, and if they complete, you don't even need to look at the waveform diagram, because when you come back 6 months later and you got to remember what it's supposed to look like. Well, in this case, we do what we're going to do, and we check. Well, I know this should be 0 here and that one in there. And I can see why. Now, you see the neg edge clock? I'll bet anything when I added these assertions, I forgot to put one of these pause edges after one of those assertions, because what I'm doing is when I do these asserts, after the reset, I don't do it on this pause edge here. In fact, that one's probably right there. I don't do it on that pause edge there. I do it on the neg edge over here. Because what I want to do is make sure that I'm looking at it after all the events and the processing in the simulation have completed. Because remember, our little game with the the non-blocking writes, this really happens later, and therefore if I did this and then immediately did this assertion, it may or may not be true that is become this value yet. Okay. We have to wait until all other always blocks finish processing the events. So what I did is I waited till there was a negative edge on the clock, knowing full well that at that point everything should have settled out, and that's what these values should be. And by saying, whoopsie, I made a mistake, I'll bet anything that I originally probably had a pause edge followed by a pause edge. Actually, that one is okay. It's the super tiny one here that I may have screwed up. I may have added an assertion in there that required a neg edge here, but I should have put this 55 over here. I'll bet that's what happened. I broke my code by debugging it. You know, how many times you have a situation where you remove your debugging and all of a sudden your program stops working? That's a good case to leave the debugging in. In any event, that's probably what I did. And what do I got here? Let's have a look-see at what happened in the code here. On a falling edge, I got a 55. So one of these things eventually will get written to a 55 in there. And I'll bet I put this in here and I put it up too high or something like that. So anyway, I just wanted you to see the style that I used in here. And while I'm poking around, let's see if I messed it up. And here I am. I'm writing a bunch of values into the registers and then make sure that they're all have the right values after we go through all these, transitions and stuff. So here's the 55. Yes, you see how there's an assert right there? I bet anything that this DN55 used to come here. My point is this probably was not here. When I added this, the 55 started appearing later than it used to. I'll guarantee you, if I look at my own Git history, this line here used to come right after that, okay? Oh, I'm going to leave it because that's the way you saw it in this video. And it's okay, provided that it gets done before this, okay? And I'll bet there's another one of those in here somewhere as well, because there was two of those little ones, right? Two of those bad boys. Where's the other one? 55 and 66. Pause edge, neg edge. Oh, yeah, exactly the same thing. I'll bet I stuck that in there after this thing. Yeah, in both cases, these things here probably belong up right after that line there. Okay? It's okay that it's this way because it does meet this. It would meet the setup time anyway, and it passes all my tests if that really happened in real life. And then over here, what am I doing? Test RM0 reset. Read mode 0. That's reading the status register. And making sure that it does reset the state. That's why we're checking this thing out and then seeing it go back to 0. And there's the read tick and so on. All right, so I wanted you to see this. This is how we should be doing them. And we also should pay more attention to if we're going to add one of these, and then after we do what we're supposed to do, not before. Okay, so let me know what you think. Thanks for watching. I'll see you next time.